In this video, I want to start looking at ways of interpreting definite integrals in the context of applied problems. Our textbook talks a lot about amount functions, which they typically designate with something like an a of t, because this is something that is changing over with respect to time. And they talk about rate functions, which we are going to designate with an r of t. And the whole idea is where the r of t function is the derivative of the amount function. So r of t is giving us the rate that a of t is changing. And under the context of this, the question becomes, what does the definite integral from a to b of r of t dt mean? Particularly in the context of the problem. Now, yeah, I already know this much. If I have a set of axes and I graph y is equal to r of t, and this is t and this is y, and we have this being a and this being b, then we already know that this chunk of area, that yellow area, is equal to the definite integral. But that doesn't tell us diddly squat about what this means in the context of the amount function and the setting that it is coming from. So I want to look at that for just a minute. And I want to remember that we have the fundamental theorem of calculus. Our second version of the fundamental theorem of calculus says that the integral between a and b of r of t dt is going to be any antiderivative of r of t evaluated between a and b. And what I want to remember is that in this kind of a problem, the amount function's derivative is equal to the rate function, and hence the amount function is a perfectly good antiderivative for the rate function. So what this means is that the integral between a and b of the rate function will be equal to the amount function as t goes from a to b. This will be the amount function at b minus the amount function at a. In other words, this is going to be the net change in a of t as t goes from a to t goes to b. Now, there is one more thing that I want to note, and that is a notational thing. So, if we have f of x, or rather f of t, is the name for the amount function, and then we will know that the derivative of f will be the rate function. And when we write this particular statement up here with these new function names, we get the definite integral from a to b of the rate function will be equal to the amount function going between a and b, and I guess that also should be a t. And this will be f of b minus f of a, and this is the net change in the amount function f of x as, well, actually, again, let me keep this consistent, and f of t as t goes from t equal a 2t=b. Now, to make this more concrete, let's look at a specific example. The example that the authors choose is this one. I encourage you to stop the video, read this example for yourself, and then start the video back up to see how we go about solving this. So hopefully you've done that. What I want to notice is that this is a rate function. It is how the usage of the electricity is varying over the course of the day. And in this particular graph, y is equal to the demand on the electricity. And y gets bigger as the demand goes up, and y gets smaller when the demand goes down. And the two questions are, is the model reasonable, and what does the shaded area represent? We're going to add a third part to this problem. How much electricity is used in one 24-hour day? And I want to look at each one of these questions separately. So let's look at whether or not the model is reasonable. Is the model reasonable? Well, here's our graph. Now, I want you to think about how electricity changes, the demand of electricity changes over the course of the day. That first peak is happening at 6 a.m. And on a typical workday, lots of people get up around 6 to 7 a.m. And as they're getting up, and you'll notice that this is probably starting like maybe 5 a.m. because the early birds are getting up then, and it's tapering off by around 6 or 7 or 8. And this part of the curve here is corresponding, and I'm going to call that part A. Part A is corresponding to people getting up. They are turning lights on. They may be turning their heat up. And in the wintertime, that's going to increase the use of electricity. They're possibly making coffee. They may be taking hot showers, which if they have electric water heaters, that's all going to go into the usage. So yeah, with all of this, usage should go up. Now, I want to think about, what about this part of the curve? And let's change this to a different color. Let's call this part of the curve B. You'll notice in the middle of the day, the usage drops, and then the usage goes back up. So we need to explain both of that. Usage goes down when people leave for work. And in the context of this problem, we're looking at a bedroom community, and so these people are working outside of the immediate locality, of the immediate community. To put this in context of Buffalo, this particular suburb might be someplace like the town of Tonawanda, and many of the people in the town of Tonawanda drive into Buffalo for work. And so the usage drops a little bit during the middle of the day. It doesn't drop excessively because there are people coming in to work and there are people still at home and things like that. But now, what about this part of the curve over here? Well, this is corresponding to 18 hours is 6 p.m. This is the dinner hour. People are home. They cook dinner. They're watching TV. They are putting their kids into baths So you're dealing with kids. There are lots of lights on. There's lots of computer usage. Again, usage should go up. And then finally, at the end of the day, usage is going back down as people go to bed. That's why we see the big drop, particularly after about 10 p.m. So, is the model reasonable? The short answer to that is yes, the model is reasonable. And if you're asked one of these kinds of questions in your homework, we want you to put in this kind of writing to explain why you think the model is reasonable. Well, let's look at the next question. The next part of this question was, what does the shaded area represent? Well, let's see. Mathematically, the shaded area is the integral between 0 and 24 of the rate function. And that is going to be the amount function as we go from 0 to 24. So this is going to be the amount of electricity used in the 24 hours. So this represents the daily electric use. And we have to think about the units. If this graph is being drawn, y is equal to r of t, and this is megawatts per hour, then the electric use is going to be in megawatts. How many megawatts of electricity does the community use in one single day? That's what the shaded area represents. Now I want to go to that third question that I posed as well. How much electricity is used in one 24-hour day? Well, we already know how to compute that. We want to be looking at the integral between a and b of r of t dt, and a is actually 0 and b is 24, and r of t is that function that is shown right here. So the total electricity used in one day is given by the integral between 0 and 24 of this function, 4 plus sine of tiny little number times t plus 4.7 plus cosine of 0.526 times t plus 9.4 dt. And I usually put big brackets around the integrand. Now I want to actually look at this function that we're trying to integrate. It's got three parts. This part is easy to integrate. This part is the sine of a linear function. It's important to realize that what we've got here is a constant times t plus another constant. And over here we're integrating the cosine of a linear function. And that is a linear function because, again, we've got a constant times t plus a constant. So both of these two pieces of the integral are undo the baby chain rule type problems. And we know how to do that from a previous video. So when we continue our work, we are going to get 4t. The antiderivative of sine is cosine, but we have a linear function, so this is going to be cosine of that same linear function. Divide by the slope of the linear function. And the slope of that function is going to be that number there. And then we're going to have to find an antiderivative for cosine. But the antiderivative for cosine is known to us. That is minus the sine. But we're not looking at the cosine of t, we are looking at the cosine of a linear function of t. So undoing the baby chain rule says that we are going to have minus the sine of the same linear function divided by the slope of that linear function, and the slope of that linear function is that number. And we need to evaluate this mess between t is equal to 0 and t is equal to 24. And what this means is that we first of all plug in 24 for all of the t's. So we are going to have 4 times 24 plus cosine of 0.263 times 24 plus that 4.7, and then we need to divide that by 0.263, and then we're going to do minus the sine of 0.526 times 24 plus 9.4, all divided by this number here. And then we have to actually plug in 0 and subtract off the answer when we plug in 0. And it's important to realize that neither of these terms is going to be a 0 when we plug in t is equal to 0. So I want to formally write out what that's going to be. We're going to have 4 times 0, which is going to be a 0, plus the cosine of this number here times 0 plus 4.7, all divided by this number here, minus, and then we look at plugging in the 0 for t in this term. So we have minus the sine of 0.526 times 0 plus 9.4 all over 0.526. Now, when you think about plugging this into a calculator, it's important to realize, and I'm going to do this kind of sloppy, that particular term is going to go to 0. This stuff here is going to go to 0, so we're going to be looking at the cosine of 4.7. This stuff is going to go to 0, so we will be looking at the sine of 9.4. When you evaluate this thing, you should get a number that is approximately 95.781, and our units are megawatts. If you do not get this number when you evaluate it correctly, chances are your calculator is set to degrees and it needs to be set in radians.